Hello everyone, welcome back to Energy Conversion System 1. My name is Rido Irwansha, and in this video we will talk about the axial steam and gas turbine. Previously we've studied about the axial compressors. Now we will proceed to the chapter where we will talk about the axial steam and gas turbines. In some books they separate these two types of axial turbine into separate chapter. But for this video, we will talk about these two types of axial turbine in the same chapter. The story of the axial turbine began around the late 19th century, around 1880, when an English engineer back then, Charles Parsons, began to develop an axial steam turbine for marine applications. Nowadays, the axial steam turbine are mostly used for the power generations, where steam type of axial turbine can work for applications that able to generate between 600 to 1000 megawatt of electricity. On the other hand, the gas type of axial turbine are mostly used for the aviations applications for aircraft engine, for example, but also for power generation. And in this video also we will divide the sections of the video into 4 different sections. First, we will begin the video about the turbine stage, and then we will move to the stator and rotor losses, and then we will see the reaction ratio, and then we will finish this video with the blade types of axial turbines. Before we begin with the turbine stage, we can also classify the axial turbines into 2 different types. First, we can classify the axial turbine as the impulse type, and then secondly, we can categorize them into the reaction type of turbine. In both type of turbines, the pressure will decrease across the stator and rotor. However, the velocity will increase each time it passes the rotor. So in general, both share the same characteristics. And to proceed with the discussions, we will combine the analysis for both gas and steam turbine in this video. To discuss about the turbine stage, we have the same principle to that of the axial compressors, where a stage means combinations between stator and rotor. And also please keep in mind the numbering systems that we use 1 to define the conditions at the outlet of the stator, and then we use 2 as the conditions at the outlet of the rotor. And we have alpha as the absolute flow angle and beta as the relative flow angle. Both of these angles are measured to the axial directions, where we have dashed line here to represent the axial directions of the flow, and we know that the inflow, or U, is perpendicular to the axial directions. First, let's assume that airs enter the stator row at C0. This is the absolute velocity at the stator inlet at an absolute angle of alpha 0. And then the air leaves the stator at absolute velocity of C1 at absolute angle of alpha 1. And it moves through the rotor blades, and then it leaves the rotor at absolute velocity C2 and absolute flow angle of alpha 2. As the air passed through the rotor blade, we can see that the absolute velocity from C1 before it enters the rotor will be reduced into C2, and also during this process, the pressure is also decreasing. On the other hand, we see that the relative velocity is increasing as it leaves the rotor blade. Now we call this as a single stage analysis for velocity triangle, and then these conditions at the rotor exit will be the conditions for the inlet for the next stator blade. For further analysis, we will combine both of this velocity triangle, or we superimpose them into one velocity triangle, as they share the same blade speed, or u, and we will continue with this kind of velocity triangle in analyzing, for example, the work being done per unit mass flow rate and so on. To further analyze the turbine stage, we need to look at the energy transfer equations that we know E is equal to the blade speed, as we know that U is constant throughout the rotor and stator, and it is multiplied to the Cx1 minus Cx2 divided by gravity. And we also have to acknowledge that Cx2 is in the negative x directions to that of the blade speed. So to further calculate the amount of work done per unit mass flow, we can combine the energy transfer multiplied with gravity. So this one moves here. We have E multiplied with the gravity accelerations, or it will be equal to work divided by the mass flow rate. That will be equal to the blade velocity multiplied with the sum of Cx1 plus Cx2, or the tangential component of the absolute velocity at both the inlet and outlet of the rotor, or it can also be equal to the u multiplied with the sum of the tangential velocity of the tangential component of the relative velocity at both the inlet and outlet of the rotor. Moreover, from the velocity triangle, we can see that the axial component can be, or it is safe to assume that the axial velocity will remain constant across the rotor and the stator, so that Ca is constant. So we can calculate the work per unit mass flow as a function of blade velocity, the axial velocity multiplied with the tangent of alpha 1 plus tangent of alpha 2, or we can look them from the relative flow blade angle, or the relative flow angle at both inlet and outlet of the rotor. This equation is often known as the diagram work per unit mass flow. This will lead us into another terms that we will call as the diagram efficiencies. The diagram efficiency is a ratio between the diagram work done per unit mass flow divided by the work available per unit mass flow. The easiest way to describe the diagram work is it will be, or it can be represented as the length between this point to this point. We normally call them as diagram work. And to get the diagram efficiencies, we can get them from, or by multiplying the blade velocity with the sum of the tangential component of relative velocity at the inlet and outlet of the rotor, or Wx1 plus Wx2, divided by half of C1 to the power of 2. From the thermodynamics point of view, we can also analyze the turbine stage by looking at this Moye diagram with an enthalpy and an entropy of the gas that moves through the rotor and stator. where the air or gas or the fluids at the inlet conditions are at total pressure P00 here and total enthalpy of H00 or here. As the fluids move through the stator in adiabatic conditions, thus the enthalpy will remain constant between H00 to H01. And this explains the conditions between the inlet and outlet of the stator. However, since the process is irreversible, the pressure will drop from P00 to P01. So this is the total pressure at the outlet of the stator, P01. As the fluids move to the rotor and the expansion process occurs, the pressure will change from P01 to P02 at the enthalpy of H02, and this process occurs across the rotor roll. From these conditions, we can get the work done per unit mass flow across the rotor. That work divided by the mass flow rate will be equal to the difference between the total enthalpy between 0.01 to 0.02, or between the inlet and outlet of the rotor. Or we can calculate them by using the specific heat and the temperature change across the rotor roll. And we can also combine these equations with the equation from the previous slide, where we know that the work done per unit mass flow rate is also equal to the function of u, axial velocity, and the sum of the tangential value or tangent value of beta 1 plus tangent of beta 2. And combining these two, we will get them as a functions or a new equation, so to say. And from this, we can get the turbine stage total to total isentropic efficiencies, which is a ratio between the actual work to the isentropic work, or it is a functions between the temperature difference T00 at the inlet of the stator and T02 at the outlet of the rotor, divided to the T00 to minus T02SS, or the conditions here. This represents the isentropic work, and this 2 represents the actual work. We can also use these total to total isentropic efficiencies to calculate another parameter that we know as the decrease in stagnation temperature, or temperature difference between the inlet of the stator and the outlet of the rotor. It is a function of the total to total isentropic efficiencies multiplied with the temperature at the inlet of the stator, and we multiply them to the functions of 1 minus the pressure ratio between the outlet of rotor and inlet of stator to the power of gamma minus 1 divided by gamma. Please keep in mind that gamma is a function between Cp and Cv,